Okay, so this is going to be the end of chapter 1. Okay, and then we'll start on chapter 2. So I'm sorry for missing class today, but hopefully this will help us get back on track, and we'll be ready to go on Wednesday. And so this is going to be made available to you through a YouTube link, and you'll be able to watch it that's not how you spell YouTube, as many times as you would like. I don't know how to erase. Okay. So to finish chapter 1, we're going to finish talking about the International System of Units. And so one of the things is what a derived unit is. So if you think back to table 1.2 on the slide before the prefixes, there was a list of 7 base units. And so these are also called fundamental units. Now, a derived unit is a combination of the base units. Okay, so volume is an important one, and it's one that we see the most often. And it describes the amount of space that a given substance occupies. Okay, so but it's a derived unit, and it's kind of hard to visualize why that is the case, and so I'll show you on the next slide why it is. So on this slide right here, we're addressing why volume is derived. Okay, so this is a perfect cube. It's made up of 1,000 cubes. But you can see here that in the very tiniest one, okay, that it's saying that it's 1 cubic centimeter, which means it's 1 centimeter by 1 centimeter by 1 centimeter. And when you take the volume is 1 times 1 times 1, but you also multiply the centimeter units, which makes it 1 centimeter cube. And that's 1 cubic centimeter. Now the thing is that we don't usually use cubic centimeters in the metric system. We use milliliters. And so the relationship between cubic centimeters and milliliters is 1 cubic centimeter for every 1 milliliter. Okay, so getting back to why it's derived. Well, it's derived from length measurements. Okay, now that only works when we have a perfectly describable shape by a math formula. So like a cylinder is another example. Rectangles, things like that, cubes. I would guess even probably like maybe a cone we could calculate. But for the most part, we're not going to have regular shaped objects. Like what about your desk, right? So your desk is not a regularly shaped object. So how do we get the volume of something like that? Well, it gets a little more complicated. Now, we're going to talk at the end of this chapter about this, kind of the idea of converting between the English system and the metric system. And so these are some important conversions, but what you can't see off to the side that says do not memorize, okay? I will give you a conversion sheet that will have all of the important conversions that you will need on the test day when it comes. The only thing is you need to know how to use them. Okay, so you need to know how to use them. Yes. But memorize them? No. Alright, so some other units that we may see that are not the base units are energy and density. These are also what's examples of derived units. Now, energy is most often used when we're talking about the ability to do work, and so sometimes it's nutrition. You may remember things like calories, lowercase calorie, because there's uppercase, lowercase, kcal. But in chemistry, we tend to use it in the terms of joule, and so joule is pronounced like joules, okay? And it is the SI unit of energy. So how much energy it takes to be able to do work, like push a desk or walk up some stairs, or in nutrition, it has to do with digestion or a biological process. Now, density is important to us. It's also a derived unit because it is the relationship of mass over volume. Okay, so it's often shown this way, or another relationship that's also true is density times volume is equal to mass, okay? So it's just simple algebra rearrangement. Now the units for density vary a lot, and so you'll see the examples here. So grams per cubic centimeters are used for solids. You also see grams per milliliter. This is probably the most common. But then every once in a while we also see grams per liter, and this is typical with gases. So when we talk about the solubility of gases, if you've ever looked at like the gas levels in a blood sample test, they're usually, they have special units for gas, and it's how much gas is dissolved in a certain sample, whether that's O2, CO2, etc. Alright, so converting units is something that we are going to need to practice, and we will practice it together on this slide, and then we'll spend time in lab doing it as well, and your sapling homework will have you practice it. But what we need is a conversion factor, and this is what I told you didn't have to memorize. And really it's a relationship between two things, like 1 inch is equal to 2.5 centimeters. So say I measure something with a ruler, but I need to know what it is in the metric system, well then I can convert and then get my answer. So we represent them like this. They can also be represented as a fraction, because the equal sign means they are related in that way as well. And so we can express it either which way, okay? And when we have it in this form, we can use it for conversion problems. So the one thing is we have to talk about the exact number. So a few slides back in class, we talked about sig fig rules. Well, conversions are exempt from counting sig figs because they are considered to be exact numbers, and these are things that are defined, like as in conversion factors, or things that can be counted, like I have 12 eggs. Okay, it means exactly 12 eggs, right? There's no uncertainty with things that can be counted. So when we do conversions and we want to check for sig figs, we do not have to worry about the conversion factor. They are not part of this process. Okay, so this is the key right here. It's called the concept map. And you can see here, this is the problem in version 2.0 we're going to be working on, and then this is page 35 through 37 in version 1.0 for the problem that we'll do on just a few slides. So say I'm in meters and I want to my answer in centimeters. Well, I have to put what I'm converting from on the bottom and what I'm converting to on the top. Okay, and so we'll practice that in just a little bit. Alright, so the conversion factor is going to be expressing it in the numerator and denominator fashion, and let's go ahead and start practicing these things. Alright, so the first one, I apologize for the book, but you can see the page numbers. It says, give the abbreviation for each unit and define the abbreviation in terms of the base unit. So the first one here is kilometer, so kilometer. The second one says milligram, so lowercase m and g for milligram. You don't have to underline. I'm trying to enunciate what I'm writing. The third one is nanosecond, so nano is N, second is S. So remember SEC, nope. So nanosecond. And the fourth is centiliter. Okay, so lowercase c, uppercase L. And so remember, liter must be uppercase. And then the ones that people tend to get confused here are micro is an M. Is a Greek mu. Milli is an M. And mega is a capital M. And same thing, kilo here is lowercase. I just want to make sure it's clear on my writing here. Okay, so these are the three that people get the most mixed up on. Okay, so it's kind of like translating. That's what I think of this as. It's just translating from one language to another. Alright, the one down here says, what is the density of oxygen gas if 15 liters of a sample has a mass of 21.7 grams? So when I do problems like this, I usually will start writing over it like that's density, that's volume, and that's mass. And so then when I can see my variables, I can see that the density is what I don't know, or what I need to know. The volume is given to me, and then the mass is given to me. And then if I think back and I look at my equation sheet, which you will get an equation sheet for the test, okay, with all the pertinent ones, and maybe some extra ones that you may not end up needing. Okay, so it won't be we're going to use everything. So when I get this, I could easily see, okay, I have this right here, this formula. It's got two variables that I know and one that I don't know. And so it's a simple plug and chug, just making sure, 21.7, making sure you plug in the right numbers into the right places. So I showed you a good example of a potential mistake you might make. And then we're going to divide 21.7 by 15, and it's going to give us an answer of 1.4467 liters, okay? But sig figs, this is a division problem, so I have 3 sig figs here, 3 sig figs there, so this answer can only have 3, okay? So I need to round up using the 6, which is going to give me 1.45 liters, okay? We will continue to practice this concept in the coming chapters, so do not stress if this doesn't make sense, but please rewatch it or ask me and I can find you additional YouTube channels or things like that to help you. Alright, so now this is about metric system conversions. Okay, this is where you need to know that chart that I told y'all about in the last lecture, I think. Excuse me. It's table 1.3 in the old version, and it's table 17.3 in version 2.0. Okay, so this is going to ask us to convert from 101,000 nanoseconds to seconds. So I'm going to start here, 101,000 nanoseconds, and I need to go from nanoseconds to seconds. Okay, so if I write it out this way, what will end up happening is the nanoseconds will cancel out, and I'll be left with seconds, which is what my final answer needs to be. So in this case, I need to look at my table here, and I see that for every 1 second, there is 10 to the 9th. Gotta make sure I got that right. My brain is not working as well today. Okay, table... Yes, 10 to the 9th, okay? So this is a smaller measurement, so there should be lots of them in this 1 second, okay? So when I do this problem, I'm going to end up getting, taking, it looks something like this, times 1, and I'm going to divide that all by this, right? Because these will multiply by each other, but then the bottom and the top will divide, okay? Oh no, sorry guys, zoom back out. I don't even know how I did that. So, with that, I have to do this in my phone. It should be okay. And so remember, this is where you want to make sure the fives, or your seconds and your fives don't look alike. All right, the next one is 32.08 kilograms, and I want to convert kilograms to grams. To grams. So this will allow kilograms to cancel out and will leave me with grams for my final answer. So if I go back to that table, I can see that every 1 kilogram has 1,000 grams in it. So then I'm going to 32.08 times 1,000, divide that by 1. So I'm leaving out the units here and I'm only putting the numbers. And so 32.08 times 32 is 32,080 grams. Okay, 4 sig figs here, 4 sig figs here, 3 sig figs there, 3 sig figs there. Again, we will keep practicing these. Lots and lots and lots. All right, one more. This is using dimensional analysis to solve this problem, or we can use our density formula. So I'll show you both ways here. So this says, what is the volume of this mass if the air's density is this? So again, I can look at what I don't know, what I do know, and then what I do know. Okay, and so I could plug it into density equals mass times volume, but since my volume is what I need and it's not solved for, I will have to rearrange it. So that ends up being volume is equal to mass divided by density. Multiplied this to the left and then divided out density to get it back to the right. And so now I get this arrangement. And if I divide 100 by 1.3, you should get 76.92. And then the grams will have canceled out, leaving me with liters. But because of sig figs, we're going to say that the volume is 77 liters, because this is 2 sig figs, so I can only have the first two numbers. Now, if you don't like that, dimensional analysis is nice because if I want to end with liters, I have 100 grams, and I can treat the density like a ratio. It's 1.3 grams for every 1 liter, and the grams will still cancel out, and I still get the same answer. Okay, so even if you can't remember a formula, you can usually use dimensional analysis to get the units to cancel out. Okay, we are going to move on to chapter 2. So you'll see this one loaded up, and then chapter 2 will be next.